And good evening, depending on where in the world you are connecting to our AI webinar series. Before we get started, I would like to thank our sponsors, University of Maine AI Initiative, as well as IEEE Maine section of Computer Society and Communication Society joint chapter. So please note that if you have questions during the talk, you are welcome to enter them as it comes to your mind into the Q&A session, and we'll have time at the end of the talk to go over the Q&A. So without further ado, I would like to introduce our speaker for today. Dr. Crystal Maraj is a research assistant professor at the Institute for Simulation and Training at the University of Central Florida. She received her bachelor's degree in psychology and master and PhD modeling and simulation from UCF. And for the past 4 years, she has worked for the Simulation and Training Technology Center as a researcher on medical simulation technology project, as well as developing and implementing empirically based research experiment for simulation-based training platforms. Dr. Maraj has published research finding to inform the scientific and training communities to improve trainee performance and trainee system utility. And most recently, she has been leading the realistic assessment of performance in devices in Rapid Lab that focuses on the evaluation of virtual reality and augmented reality technologies that assessing capabilities, deficiencies, specification, cost, maturity, and risk. This information will help inform the community of the technology readiness level of different devices. And of course, in addition to leading the Rapid Lab, Dr. Maraj also manages the robotic lab at UCF, and she mentors the students as they prepare for local and national robotic competitions. Her interest in outreach program has led her to actively participate in STEM activities that support Florida school community. So without taking too much time, I would like to welcome Dr. Maraj to the podium, and thank you so much for accepting an invitation.
Of course, and thank you. Good morning, good afternoon, good evening. I just wanted to introduce myself. My name is Crystal Maraj, and as Ali alluded to, I've done a lot of work and I've worn many hats in the community, specifically focusing on simulation and training. And now with this wave of AI, we know that advancing technology, we know a lot of reshoring of our manufacturing chips. We've seen increasing in growth of our computing and processing power. We've seen AI really being integrated more so now into our technical, but maybe our less technical fields. And in doing so, it has been impacting human performance. And that's where the area I really wanted to talk about a little bit here today. Okay. So some of the introductions were covered in my abstract, but really I wanted to highlight the applied research area. So I focus on research that's conducted in the lab, but also in the field. And in doing so, what I've done is I'm able to offer recommendations to stakeholders as to the utility of these systems. My expertise area is in human factors engineering. I've got a strong background in human-computer interaction and a lot of work with human-in-the-loop testing. And what that means for when I speak with engineers is you guys want to know what's the return on investment? What is that risk mitigation paradigm? How can I help reduce costs and ultimately, at times, optimize human performance? So today's agenda, I just wanted to highlight a little bit about the lab, some of the VR, AR, XR simulation research, a newly established research area, the human digital twin, and talk a little bit about the Boston Dynamics spot, which we acquired one of those. So it's a little bit more of a breadth of information versus depth, but I think it'll definitely spark some good conversations at the end. So when we talk about this headsets for experimentation, we know there are so many headsets out there, a lot of VR headsets. We all probably have one in our homes. But with that, we're always wanting to know what is the best for what application I'm using it for. And maybe it's not for your household. Maybe it is for industry. What is the best headset used for helping for maintenance training? Or what is the headset best used for an educational setting, which can help increase learners' proficiency? So that's what we try to look at. We always try to look on the horizon to see what is out there, what is the latest and greatest, and what and how we can use these headsets for research specifically to provide those informative responses and answers. So it alluded to the slide before in talking about which system is best. So we evaluate the effectiveness of augmented reality and virtual reality head-mounted displays. And in doing so, we try to assess that readiness level. It does aid in technology decision-making, and this is definitely helpful in these three main areas for government, commercial, and academia. Just knowing this information is very important because we talk about the decline of budgets. We're talking about so many competitions when you have these headsets available. You really want to hone in on what headset makes the most sense for what you're trying to accomplish. Okay. So the technical maturity slide, it's interesting because when we look at here, we're talking about that technology readiness level from scale 1 to 9, and then also that manufacturing readiness level, again, 1 to 9. And so when you're doing basic research or we're in the field of academia, we usually stick around the TR levels 1 and 2. Time to time, we do move up a scale depending on the type of research that we're doing and is funded. And the same can be said for manufacturing readiness levels. It's important to know the type of system that is available. For example, I know the IVAS system. It is one of those headsets where everybody's talking about. It's the headset that the military would like to incorporate in some of their missions. And they're trying to figure out how to scale. But before they scale, they have to figure out some of the human elements. They are running into issues of simulator sickness. They're also running into issues of nausea, oculomotor, and disorientation. So you've got to work through those elements first before you start scaling some of these systems. That is imperative when you are looking at deciding if I want to have a HMD that's basic research, or I want something where it's deployable and ready to launch. So what we do in the lab is really a 30, 60, 90-day approach. So what does that mean? Essentially, we take a head-mounted display, commercially available off the shelf, we go grab it, and we take it out of the box. And what we do is a basic fact checking, so verification and validation of certain technical specifications. So for example, if the headset says, I have 180 degrees field of view, is that really 180-degree field of view? What we do is we develop a battery of tests to test that and actually determine whether or not it's a true field of view. Other specifications include weight distribution. We look at latency. We look at whether it's tethered or untethered. But some of those factors are driven into that 60-day battery of tests that we've developed that we use in our labs to test that certain specifications that have been put forth by the 30-day. And then the 60-day will give you that test, but we use a small sample of participants just to get more of a baseline of how that data looks like. And then the 90-day gets into that evaluation where we involve a larger sample size of humans, and we have them use different head-mounted displays, and we get ratings based on how they perform. And that includes objective data as well as some subjective data. So I just wanted to highlight a little bit of the field of view test that I picked just to illustrate how this is done when you are trying to evaluate from a perspective of, is it true or is it incorrect? So we developed a test, and I will show you really quickly what the idea is. You look straight at a particular circle. You'll then look left, right, up, and down, and it captures that data points. Data points is then it is expelled into an Excel spreadsheet of then which we then take and we can computate the true field of view. So I will hit play and you'll have an idea. So you capture left, wait for that recalibration again. You look to the right. Captures. Up and then down. Okay. So in that example, we were able to capture that data point for a few people that participated. And what we found was when we looked at the horizontal field of view for the Oculus, it resulted in actually a lower field of view, 93 degrees. Similarly, for the HTC Vive, marketed view as 110, very similar to Oculus, it actually improved. They had a little bit wider field of view. So why does that matter? Well, it matters because if you're completing live or simulated training events, a live example, if you have a headset on and you're completing maybe a walking task, you probably want to have a field of view that's similar to your own field of view, right? The ability to have that situational awareness versus, let's say something, for example, a simulated training in a tank, where you may have a small field of view and you don't necessarily need to have such a large scale viewpoint. And so that might be a consideration when you're looking at these types of headsets for utilization in different areas. Okay, so the 90-day evaluation, looking a little bit at the usability element, when we look at different headsets, we want to see how they perform, as I mentioned, from an objective standpoint and a subjective standpoint as well. So the idea of measuring effectiveness, efficiency, so your time-based durations, completion rates, these are some of the metrics we look at when completing a specific task in the simulation. And equally to objective, we do capture subjective measures. So you do want to know a little bit about your participants. So we capture demographic information, workload from time to time. If we're looking at the NASA TLX to measure workload, maybe effort, frustration, simulator sickness, which we know is something that's very common. We try to capture that as well. Immersion, and again, usability. And all of this is in reference to that ISO 9241. So when we talk about those usability standards, we're talking about efficiency, effectiveness, and satisfaction. And that is where our metrics were derived from. So I wanted to share with you a quick 90-day simulation. I think this was one of our Meta headsets, just to kind of illustrate what you would ask a participant to complete when we were capturing these data points for the 90-day evaluation. So we were collecting those objective metrics and those subjective metrics as well. But this just happens to show you the simulation in play. I wasn't very good at this task. But, okay. Okay. So that's just to give you an example of our 30, 60, 90-day process of what we do in our lab. So one particular initiative we looked at was the Vive Pro 2 and the Oculus Rift. And we wanted to assess whether or not there was usability differences, subjective and objective, between these two headsets with their respective controllers through a specific teleportation task within a virtual environment. So for definition, we talked about virtual reality. What we're talking about is that synthetic environment that is created within a artificial environment, and it does have elements of real world constraints. So the idea of time passing, or the idea of you are still influenced by gravity, so your feet are on the ground, helps to create this level of psychological fidelity. Okay. So it drove our research questions. We wanted to know if there was a statistically significant difference in objective usability, which was measured by per scenario effectiveness, time duration, total time duration, completion rate, time-based efficiency. Again, those objective metrics I highlighted before between the two systems. Also, we wanted to see if there were differences in the subjective usability. So ease of use, comfort, visual quality, effectiveness. So again, the subjective usability is that person's viewpoint, their perception of the system. And we also wanted to example for research question 3, if there were any correlational relationships between subjective and objective for the two particular systems. So this slide just highlights the a little bit about the operational definition when we defined effectiveness, ease of use, comfort, visual quality. Again, that is that user's perception of how they felt they completed the task, how they felt it was easy enough or required little effort, if there was a level of comfort and visual quality in terms of the clarity of images. We asked their perception of that. And again, more objective data that was captured during these experiments. We looked at, as I mentioned, 5 of those listed items, but with the idea of the objects collected, although the total number they captured, the start and end of these scenarios, and a combination of how many scenarios they were successful at, given the total number of scenarios. Okay, so for this particular effort, we had 40 participants, 14 were males, 26 were females. They were UCF students, so basically main campus. Age range from 18 to 30. The inclusion criteria was they had to have no previous history of seizures and had to be of good standing in terms of health. We compensated them with $10 per hour, and it was about an hour study. So we were looking at the differences between those two headsets and trying to understand some of the usability data that were outputs. So the test battery, they used the teleportation locomotion controller to collect a set number of objects within that 5 to 10 minutes per scenario. And the scenario included a room, so you may have seen a forest or village. So it started to increase in complexity. And then highlighting the test bed, that we use the operating system for completing our experiment using these HMVs, and then highlighting the procedure. So it's very constant, it's very direct, and we try to control for as much as we can. So there's a systematic process. You get your informed consent, color blindness, demographics questionnaire, the VR interface training. They then completed 3 scenarios, as we mentioned, about 5 to 10 minutes long, 1 minute break between each. And then they completed the usability surveys, receipt for compensation, and they were then dismissed. So I just wanted to provide a screen grab of what the simulation looks like. As you can tell, it's very simple all the way to complex. There was timing involved, and they were asked to teleport from one blue object to the next, brightly blue object to the next. Same for scenario 2 and 3. So when we looked at the results, we had to use non-parametric tests. The data was not normal, so we had to use the independent sample t-test, which was a non-parametric version to that, which would have been our Mann-Whitney U. So when we talked about the differences in objective usability, we wanted to know if there was a difference between the two systems. And what we found was that there was a difference between the Vive and the Oculus when it pertained to scenario 3 effectiveness. In regards to research question 2, in terms of subjective usability, there was differences between the Oculus and Vive for effectiveness, for their perception of how they felt this device would actually work in the real world skills if they had to use them. There were differences between the two. And then in terms of the ability to use a wide range of application, they felt that there would be differences between the two systems. And then research question 3, looking at the correlational relationships between these two systems, we wanted to examine, is there a positive or negative relationships and where did that fall? So as you can see, the the Vive actually had a positive correlation for the most part as it relates to comfort and being time-based efficiency. So higher comfort, higher the amount of time or the less amount of time they took to complete their tasks. In regards to ease of use, we saw that both systems, Vive and Oculus, they were viewed as easy to use and again having a positive correlation with that time-based efficiency. Effectiveness, we seem to have had a positive and negative correlation for the Vive. And then visual quality, you can see again back to efficiency. The better the quality, the better, the more efficient the individuals were in completing the tasks. So what does that mean in terms of the systems? What we can tell you is that the Vive Pro seemed to have better efficiency, effectiveness, and overall satisfaction. The Rift, while it's not while it has its challenges, it can probably improve and can be used, but it might need some performance aids. So you might have to use highlighting or prompting within your scenarios that may help the user perform better if you had a Rift system. In regards to research question 3, as we look at the system correlations, comfort was a plausible indicator of high completion rate for the Vive. The quicker completion rate might be usable in some scenarios, such as if you were to look at a virtual rehabilitation or maintenance training. That might be an area where those 2 points or those 2 components matter. Interestingly enough, we saw the reversal between visual quality and time duration. So the better visual qualities, as we saw before, the quicker they completed their training. But what happens in a situation where you have very compelling visuals or very high fidelity visuals? That could perhaps impact your learning. So it's worth another investigation in that. So we've done simulations for tasks that surround walking, depth perception, pick and place, teleportation. I try to give a screen grab or at least a video of a combination of these. What we're trying to look at next is the Magic Leap 2 versus the Apple Vision Pro, which has just been released. I don't have it yet, but this is definitely one area we would like to see and explore some of the motor skills, maybe coordination and dexterity. It's definitely one area that's had a lot of talk about. From what I've heard so far, I've heard the headset, the Apple it's very front heavy, so that's something to think about. It does take up a lot of battery life is probably very short. So these are the kinds of things that I've been hearing, at least on YouTube, and it has been trending. But it will be interesting to see how these 2 systems perform in a research activity or research setting. Okay. So I explained the combination of 30, 60, 90, collecting different types of data from usability to technical evaluations that would have captured, again, field of view data, latency. We've captured other items such as trying to assess maybe the ruggedness for IVNV, glove-based interaction, eye tracking, hand tracking. Haven't done too much research on the head tracking. Video pass-through, optical see-through, another area of consideration. And we've captured these data, but again, always looking at maintaining that horizon awareness of what else is out there. So what that has done is it makes me think of the human processing model, and I'm going to get to the AI component. Now, as humans, we have a visual stimuli, we observe, we analyze, we compare. There is a match or no match. What happens is during these processes, we as humans, we think about change blindness. We go through that process, change detection, perceptual training, perceptual thinking, information processing, pattern recognition, which we engage in. We pull into our long-term memory, sometimes short-term working memory. And all these helps to create that decision point, right? And then we make that point if it's a match or no match, in this case for pattern recognition. So what is interesting is that AI can simulate human reasoning and provide that information processing and decision making. And so the more accurate or fidelity our information is, we can have more objective metrics in order to help assess with some of these evaluations. So what does that mean? So essentially, we've been capturing these data points. So we have sight, sound, touch from these HMDs. We're looking at individual and then group training. So essentially, a lot of these headsets can be used in group setting in order to collect collective training information. We're looking at specific task domains. So psychomotor, cognitive, decision making, just to name a few. And then your consideration of that headset and the different components and ideas and concepts of what they focus on when they produce their headset. We capture that information based on the HMD that has that already embedded. And what it does is we go through this process where we complete that technical evaluation and human in the loop evaluation. And then it gives us our outputs, right? It tells us which system might be better. It tells us which system may result in backache or neck strain. It may even give us headaches. So we have that information, that output. And what's interesting is, and this is where the AI implication comes in, is you've got that output from before, right? You've got the output from here that's driven. But what this then does, it creates this new input that we can plug into our AI and then have that machine learning, that deep learning, the neural networks create and foster that modules or those decision trees that will give us a predictive element. And that can be considered our output. And that's where we do have these implications, because we've got all this data that we've collected. But what can we use with this in terms of helping understand where AI can help us move to the next step in terms of potentially predicting performance? And so, the AI implications are the ability to enhance clustering of individuals and teams. So groups that might be similar, they perform similarly. We want to be able to assess where their competencies are and then highlight areas maybe where they can improve. Having such data would also help us to identify patterns in that perceptual data. So simulator sickness and usability, we can try to identify ways to optimize performance, but reduce simulator sickness, which has been, as I mentioned, one of the areas that has been really some exploration has gone in, but not enough. But maybe we can understand how it relates to field of view, latency, and visual display. That is also a driver for some of the feature selection, identifying specific information or characteristics that may help make inferences, and then understanding some of the highest contributing factors, which will be able to maybe maximize or enhance their performance. And pointing out that it is a little bit different when we talk about the AI implications and mentioning the idea of embedded training. And I know we've talked about adaptive tutoring in our day-to-day, topics. And this is a little bit different because when you talk about embedded training, we're talking about getting that information in real time. But does it help with learning per se? What I'm doing is I'm presenting the information that you might need as an individual at that point. But measuring the idea of learning and engagement, it takes it a little bit one step further. When we talk about the AI implications moving further, it does allow the ability to create a personalized learning path. So now what we can do is now you can anticipate probable future students and how they are learning. And what does that mean? So we can evaluate some of their levels of mastery based on some of those inputs that we can then put into that box. Understanding that we may have to recommend certain types of practice or training exercises to enhance performance, or it may also highlight the area where you need to forego some of those training points because it may not help you. It may not add any value to your learning journey. Okay. So this kind of switches a little bit into another effort. I'm the co-PI in this particular effort, but I think it's important to at least have this conversation about the idea of human digital twins. So a digital twin is a virtual representation of a product or process, right? You think about it, tanks, buildings, cars. You can basically create a digital twin. The novelty of this particular research is the human element, which uses this fundamental AI tool to help the user in making better decisions with a specific interface and within a certain scenario or context or within a physical structure. Current human digital twins, it's more in the conceptualization phases, if you will, and it has not been realized. I actually had a conversation with students and they're asking, oh, what has been the progress on this? Do you have things that are interfacing with you and things where you get information and details and how much of it is, reliable? We haven't gotten to that stage yet with this particular effort, but it is good for just stimulating some, like as I mentioned, some conversations. So part of that is that interface. And what does that interface look like? You've got a human digital twin. You have information coming in from maybe different systems, different products, different processes, and all this information is presented to the twin. Plus, also the data from the humans. So your cognition, metacognition, maybe it is workload, all of this information is coming in. So what does that information look like on the receiving end, right? The output. So there is research that needs to be done as to what that looks like. So to really break down what that looks like, we had to talk a little bit about the different research areas. So we talk a little bit about cognitive learning. So we have to develop learning models to interface between the human and then the human digital twin. We have learning models, cognitive architecture such as ACTAR and SOAR that can help feed that cognitive learning. Artificial intelligence piece, this is where we do have that predicting element, that deep learning that comes into play so that it can help understand the rationalization of why a human would think this way, but present alternatives that might be a better solution. And all of this is great, but you need to also have an immersive simulation or a simulation where you're presenting this information and the human can give you responses that are accurate, meaning that level of fidelity is important, both physically and psychologically. And so what that does is it helped us to create this particular framework where the idea is to assess human performance, but also to capture that human emotion and that emotional element. So it's going to be an interesting research area. It's very new, and we're hoping to really dissect what that framework will look like when developing this human digital twin. And it does bring to the question of how will this work, and the idea of what that interface looks like. Is this something where it is modular? Is it adaptable? Is it something that is embedded? Is it something that it's maybe a visual display with information? What does that look like? Okay, so the AI implications. So when I talk about what does that look like, maybe I guess a better scope or a better way to present that is maybe AI technology as a team member. Do we see AI and this information that is presenting as a team member? And as a human, am I receptive to that particular information? Am I going to reject when this AI member tells me it's 80% confident that this is what you need to take for your next step? Am I going to accept that, or I'm going to say, nope, I'm going to refuse that information. I'm going to do what I think is best based on, let's say, my experience. And then also talking about the data display dashboard, we want to know what does that information look like, as I mentioned. So again, very novel, very in a conceptual stage. Maybe it's a series of visual graphs, maybe it's auditory. We want to really think about what is going to go into this particular visual display. And then the fidelity consideration. So I mentioned, the human is providing data, but we want to make sure that the human element that we're putting in there makes sense given that particular environment. So that fidelity level, you want to have the right amount of psychological fidelity and the right amount of physical fidelity. Considerations for learning preferences. I mean, we all learn differently. So again, when you have that dashboard, what makes the most sense to present to the user? Is it something that's visual? Is it auditory? Or is it kinesthetic? Maybe it's something that I touch and I can get information. So again, very conceptual, but it is an idea that we are working on in this particular research area. And finally, another topic of interest, this is the robot guide dog using Boston Dynamics Spot. I was fortunate to receive an internal grant, tech fee grant, which afforded me the opportunity to purchase the Boston Dynamics dog. So it is about 70 pounds, 2 feet tall, roughly, and has about 5 cameras on him. And our students are who are in the robotics club, but some also in psychology are looking to conduct research with this particular tech. In the short term, they're looking to assess feedback, user feedback. So we talked about that trust and automation. They're looking to see assess that user feedback on 3 preset scenarios that they've done, and it's going to be guided by that robotic dog. The long-term objective, however, it's really to implement a voice-activated robot as they navigate maybe an unfamiliar terrain or territory, or even in this particular lab space, using AI, computer vision, mapping, object avoidance, and path finding. Okay, so a little bit about how it will work. It is a multi-stage process, and students are working diligently on trying to figure out the best way to guide the dog where they want it to go. For the voice command, it takes that audio information and it will turn it into text. The text, which is then interpreted by the natural language interpreter. So if we say to the dog, go left, turn right, tape measure, go straight, it will be able to register that information. But it is going to be a little bit swayed by directional biases, which we understand. So we will, the dog wants to go where it wants to go, but with the directional bias, it will, nudge it gently as to the path that it needs to go. And then we've got that path finding and then execution. I mentioned we had 5 cameras on spot, if you will, and then we do have sensors. The idea of having a 3D LiDAR scanner maybe on top to help with some of the waypoints. That's the idea, that we would then go through the object detection, digital map path finding, and then ultimately executing the particular the path that we wanted. So I believe this point cloud, a little bit of a screen grab here, kind of illustrates one of the easy paths that the robot is expected to go. So it'll start at that particular knob there, and then it will go all the way straight and then make a left, and that will be determined as an easy path. So I do have a short clip of Alex, who is working on this, the voice command application. So I'll have you take a listen. And
stop. Tape measure left. Tape measure forward. Tape measure left. There it is.
just to illustrate the point, is working on navigation. Okay. So how will it work? So we plan to use the data, visual data from Spot's onboard camera, a lot of data, audio data collected from the microphone, and then in later stages, we will have that LiDAR scanner on top, and that will help to increase that range for obstacle avoidance. The task that will be done with tape measure at this particular point is indoors, so we are doing in a lab space, but it will be interesting to see how this translates if we were to take tape measure outside. One point I missed is tape measure Spot is not autonomous. He is still controlled by the human. And you saw Alex had a picture, or you may have seen him with his computer, but on there's a little bit of a tablet, which is what we use to remotely control tape measure. Okay, so data processing using AI. So tape measure does have onboard image processing that allows him to identify world objects compared to trivial objects. We are using a large language model, but we do have a little bit of a small model specifications here, just because of the lightweight that it needs to be on his computer, as well as the quick response for commands to interpret. Students have not identified the type of object avoidance algorithm yet, but it's still work in progress. And I believe this is one of my the final slide, but it highlights the idea of the social implications for these types of technologies. So the students were developing this effort in order to assist visually aided individuals, helping them to navigate the world around them. But it also has other implications outside of that scope, maybe just for general navigation tasks. They listed examples of guiding students to new places, helping employees find different locations. And more recently, the Navy came by and they wanted to understand how this kind of technology can help them for maintenance training within their ships. So if you were to use technology such as tape measure, being able to identify when pipes or paint or machinery needs to be updated, this is one tool that can be utilized and such. And then the final bullet point, it's just showing you AI in a real world technology, and the idea of really presenting this type of tech to folks in a wider community. And hopefully it is a little bit more accepting, which goes back to the first comment that I made. AI has definitely been evolving and morphing, and it really is revolutionary. And I think we as people need to really consider what technology we are willing and able to adopt and be able to want to work with as we move into the future. Okay, final slide. I'm open to questions.
Thank you very much, Dr. Maraj, for interesting presentation. So I remind the audience that if you have questions, please put them in the Q&A and we'll answer those questions. So let's start with the first question. So how do you see any challenges in terms of like creating the human digital twin that you talk about? Is it more like you need to collect more data, or do you need more computational power to process it? So where are the current challenges you're dealing with?
So the current challenges is, what does this thing even look like for us? So we talk about this human digital twin because we use the word human, and is it necessarily a representation of a human, or is it a technology piece that can be an add-on whereby you are presenting details and information, and with that will come with computational challenges that we need to consider as well. So how much information and how much processing power we will need. In regards to the data set, we have to work with our sponsors. This particular effort is military funded, so we'll have to work with our sponsors to identify past data sets. If we cannot get data sets, that means we will have to conduct our own experiments.
Hey, thank you. So the other question is that, do you see using AI more for like creating new models for your simulation and training, or do you see that as sort of an assistive technology to help you optimize the models that you have kind of a cognitive or psychological kind of science behind it?
Yes, it is the latter. It really is more of a addition or an adaptive aid, if you will, I think when we start looking at some of those data sets, especially with all that head-mounted display data we've collected, it is taking that and generating and putting it through that model to offer solutions that can optimize performance. And it may be requiring that additional aid that you do need. You might need that particular assistance.
Great, thank you. So next question is that what is the AI that is being used with the tape measure that you just showed? Is there a particular type of AI in there?
So I think they're using AI just for the path finding element. Specifically, let's see, it's a good question. It is for it's related to that path finding, Ellie.
Okay, great. And as we are waiting for more questions to pop up, I want to take this opportunity to thank our speaker again for a great presentation. Also, I would like to mention that these webinar series are not possible without promotion from our partners. I want to thank Silicon Valley section of IEEE, Boston section of IEEE, as well as IEEE in Shenzhen, China, and IEEE in Bangalore, India, for promoting this worldwide. And keep posting your question in the Q&A. So next question is that, is there any concern in terms of like security and privacy of data when you are getting into your human digital twin?
Yes, there is going to be. So a lot of this work is funded by the military. And so we will have to set up certain types of security settings in order to create that barrier, that wall. And it really does hit on a point on the overall cybersecurity and AI, right? Because that's another area of interest that people have been getting or been talking about, is how do we acquire data without being too intrusive, right? You've got HIPAA laws, you have all these other considerations. So part of parcel is, what's the path forward that one gets you the data that you need without creating a block where you don't have any information. So we will have to, one, like I said, acquire the data, but two, there is going to be physical as well as cybersecurity setup in order to participate in that activity.
So we have two more questions.
Sure.
Before I ask the bigger question, the other one is that where we can get the slides. We will usually post the videos on YouTube, so you can also see the video and a slide later on. But the main question we have here is that, do you expect to solve the simulator sickness issue with data and software changes to virtual models?
That is the question. So I've heard that one way to reduce simulator sickness is through the reduction of that latency. That's an area, and the visual display. Those are two key areas that I've heard, and even myself, it's one of those where folks have been writing research proposals to try to get funded efforts to support that. But I think those two are pretty big. Other than I've heard people, when you talk about similar sickness, it's that the differences where the head is unable to, with ocular motor, the head is not able to have that sound, causing a little bit of discrepancy, right? So the idea is, I've heard people put a fan on individuals and have the fan blowing and saying, hey, that's one way to help alleviate. But I mean, if you're in a situation where you can't have a fan next to you, what can you do with the technology? So it really is an investigation of that visual display and that latency. If you can figure out a way to combine those two or find a way to highlight one or the other, I think that's an area that's really worth exploring.
That's great, thank you. Next question. Are you building your own models from scratch for the digital twin? If not, how do you reconcile using mainstream models that have demonstrated bias against particular genders and ethnicities for military applications?
That's a very good question. Again, because we have not explored the topic area, and maybe it was a little hard to present Ali on this particular effort, but we really are in that conceptual stage, and it is considerations that we need to think about. The data that we most likely will get would be from active military soldiers, so would be people that are enlisted. So that would be the primary data source. But yes, we do want to have those considerations in mind and be able to create decision models and decision nodes that will acknowledge at least, different ethnicities as part of its building. But it is a challenge. It is a challenge.
Very good. Thank you very much. So I think that's the all time we have today, and we covered almost all the questions. So before we close, I would like to thank you, Dr. Maraj, again very much for the great presentation. It was very broad. I think it kind of inspires people to work on so many different areas, and we are very happy to have you today. And before we close, I also would like to thank Humane AI staff, Melinda Pelletier and Dina Rice on the background to help us run this smoothly, and also our sponsors, Human AI, and also the various IEEE units. So thanks everyone for joining us again today, and see you next month in the next AI webinar series. Thank you, everyone. Have a great day.
Everyone, thank you.